Hi, in this video we are going to continue on the functional group chemistry, and in this video we are going to focus on the esters as well as later on the amide. Okay, so that would be probably the last video focusing on the functional group chemistry. Okay, so let's get started. Now first of all, for ester, the general formula is given by this one. Okay, RCOOR prime. Okay, now this one may not be the best representation. A better representation would be this one: C double bond O and then R prime R. Okay, again, the R represents the AQ groups. So these parts could be methyl, could be ethyl, something like this. And for this R, okay, it could be AQ groups, or it could be hydrogen atom. Alright? That makes sense because, like I said, for an ester, the left hand side here with the C double bond O, this one is actually coming from the carboxylic acid. So it is possible for this part to be a methanoic acid. So it is possible for this R to be a hydrogen atom. However, this part, you must be an AQ group, so at least you have to be a CH3 or something like that. You cannot be a hydrogen atom, otherwise it will become a carboxylic acid. Okay? Now, I also want you to focus on this one. Okay? This particular bond, this CO bond, we call this ester bond. Ester bond. Now, that is very important for you to be able to locate the ester bond, because later on when we talk about the reaction, it all occurs, it all takes place at the ester bond. Okay? Now, let's have a look at the functional group. So it is, the name of the functional group is called ester group. Now, all the esters are colorless liquid. And now this is very important. We often describe ester as a fruity, sweet smell. Okay? And this is the reason why esters are often associated with flavorings and perfumes. Okay? Now here we have a term called lipids. If you study biology, you should know that lipids is one of the very important biomolecules. And basically it refers to fat and oil. We should put it this way: fat and oils are examples of lipids. Okay? Now in biology we will use the word lipids, but in chemistry we will probably use the word triglyceride or even triesters. Triesters. Okay? Now they are long chain esters, so large molecules. And for this one, I try to substantiate a little bit more. For lipid or the triglyceride, they have a general formula like this. Okay, I try to show you here. So for a lipid molecule, it has, first of all, okay, so this is the general formula of a triglyceride, and as you can see, I have used it two different colors, showing you two different parts. Now, bear in mind, it is an ester, so it has to be an alcohol group. I mean, there must be a part coming from alcohol and a part coming from carboxylic acid, right? So the black part here, you see, this is not a regular alcohol. Instead, it is one alcohol molecule with 3 hydroxyl groups. So this one, we call this one a glycerol. Okay, a glycerol. Okay, and while of course this is the part coming from glycerol, this is not exactly how the glycerol looks like, but this is the part coming from glycerol. if you want to know the structure of glycerol, it should be like this. Okay. Now you remember, for the formation of ester, the alcohol part will have to, sacrifice the hydrogen atom, forming the water, right? So you can think about glycerol having such a structure, and as they undergo the esterification, they will sacrifice the 3 hydrogen atoms from the hydroxyl groups, and therefore this part is coming from the glycerol. Okay, can you see the hydrogen atoms are all sacrificed or taken away from the hydroxyl group. Okay, and then these parts, we have 3 similar parts, and this R group obviously refers to AQ group. For triglyceride, this R group you don't expect to be like a CH3 or C2H5, something like that. For fatty acid, we are usually talking about long hydrocarbon chain, and we are starting from at least 4 carbon, okay? But usually it exists as like a 16 carbon chain or 18 carbon chain, something like that. So these parts are coming from the fatty acids, okay? The fatty acids. And fatty acids are essentially carboxylic acid. They usually have a structure like this. And they got like the long hydrocarbon chain, right? Something like this, okay? And this part we kind of simplified it into alum, okay? This part we try to simplify it as R, okay? So you understand that for a triglyceride molecule, it is a large triester. Triester, as you can see that there are 3 ester bonds over here, 1, 2, 3. So that's why it is called triester. And this triester is not made by 3 alcohol and 3 carboxylic acid. Instead, they are made by 3 carboxylic acid, which is known as the fatty acids, and 1 alcohol, which is called glycerol. And this particular alcohol has 3 hydroxyl groups. So altogether, you can see 1 glycerol plus 3 fatty acid undergoing esterification, forming a triester or triglyceride or a lipid molecule. Okay, so this is the structure of a lipid. Okay, all right. Now, the physical property of ester. So, because of the ester group or ester group here, it makes ester slightly polar. However, you can't see any intermolecular hydrogen bond between the molecules, again because it does not have any hydrogen atom connected to the electronegative oxygen atom. Therefore, if you are looking for the boiling point, if you try to compare with other homologous series, ester should have a higher boiling point than alkane, alkene, even aldehyde, but they will have a lower boiling point when compared to alcohol and carboxylic acid. Okay. Now, similar to aldehyde and ketone, they can't form hydrogen bond within their own molecules, but they can form hydrogen bond with water, which makes it slightly soluble in water for low carbon esters. Okay, but when the size of the ester increases, they become less and less soluble in water or miscible in water. As you can tell from here, lipids, basically fat and oil, based on the common sense, they are insoluble in water. The reason is obvious, because for the long hydrocarbon chain, and we have 3 of them, not just 1, right? That makes it very, very large. The molecular size is very large. So the van der Waals force will predominate. And therefore, lipids are insoluble in water, okay, despite of having 3 polar ester groups. Okay. Here, esters, we are talking about low carbon esters. They are relatively volatile, which accounts for the distinctive fruity smell. Okay. Again, when you have something that is having pungent smell, they must be volatile. Otherwise, you can't inhale the gaseous molecule. Now, for chemical properties, there are just one reaction. We call it hydrolysis. Okay, hydrolysis, the Chinese name is very obvious. We call it basically decomposition using water. And from the English name, hydro means water, lysis means split. Okay, use water to split. Okay, now this reaction is again a type of reaction, and we have different homologous series, different compound with different functional group that can also perform hydrolysis reaction. Okay, so it is not exclusively for ester. Okay, now so what do you mean by hydrolysis? So the hydrolysis is a chemical reaction in which large molecule is broken down into smaller molecule by water. Okay, now at this part you may feel like it sounds familiar because previously we talked about a reaction called esterification, and we said that esterification belongs to the reaction called condensation. And what is a condensation reaction? Condensation reaction is when we have a small molecule joined together to form a large molecule, and during this process water molecule is removed. Okay, so just like here, small molecules join together to form a large molecule, removing a water molecule. Alright, so small become big, take away the water. Okay, in hydrolysis, you see it kind of like the reverse of condensation, because this time we are splitting a large molecule into smaller molecules. Okay, into smaller molecules, and in order to split it, we need water. Okay, so it's just like the opposite of condensation, and as a matter of fact, it is exactly the opposite. Okay, if you can put down here, if you have small molecule add together to form, okay, a large molecule with the removal of water, and this one would be referred to as the condensation. Okay, if you go from left to right, it is condensation. But if you go in other direction, if you go back, you use water to split a large molecule into smaller molecule. This one is called hydrolysis. Okay, so you see, this is the relationship between hydrolysis and condensation. It's just the exact opposite of one another. Okay. Now we say that esters can be hydrolyzed into their parent alcohol and carboxylic acid. So basically, like I said, ester is coming from alcohol and carboxylic acid. So esters can be split and then go back to its original alcohol and acid. Okay, but this reaction itself is pretty slow. So we don't actually react an ester with water. Instead, we try to carry out the reaction with either an acid or an alkaline. Okay? So that's why here we have two parts. We have acid hydrolysis of ester and we have alkaline hydrolysis of esters. Okay? Now, pay attention. The two reactions, even though they are called hydrolysis, they are both called hydrolysis, the reaction is slightly different. The reactions themselves are slightly different. You may consider this as two different reactions, okay? As the reactant itself is a little bit different. The reaction itself is a little bit different. Before, when we learned about reaction mechanism in A level, we have to know the difference between the two in terms of how the reaction actually takes place. It's actually quite different. Okay, even the reactant itself is different actually. Okay, now anyway, let's break it down for you. Now let's start with acid hydrolysis. So if you look at the reaction itself, it has an ester and the reactant is water. The reactant is water. Even though we add acid, the reactant is water. Okay, bear in mind. So the acid is acting as a catalyst. The acid is acting as a catalyst. So, so before, actually this reaction is called acid catalyzed hydrolysis of ester. Okay, because the reactant is actually water, not the acid itself. Okay, so under the catalysis of acid, the reaction takes place and generating an acid and the alcohol. Okay. Now, if you look into this reaction, you see I try to use different color to show you what is going on here. So, you see, it is very important that we are able to locate the ester bond, which is here, because hydrolysis is splitting or decomposition of a molecule, right? So we try to locate the ester bond and then we cut it. Once we cut it, then the water here, the water, we can describe it as, using this bond line structure, and we say that the OH here, okay, will be inserted into the acid, whereas the H here will be inserted back to the alcohol. Okay? Now, if you remember for esterification, we have a similar discussion, right? We say that the carboxylic acid will provide the OH, the alcohol will provide the H, the OH and the H combines to form a water, which results in as a product. Okay? Like I said, hydrolysis is just the reverse of esterification. So here, when we split open the ester at the ester bond, we actually have to insert the parts back to the acid part and the alcohol part. So that's why you see over here, the carboxylic acid, the OH here, is actually coming from the water, and here the H is coming from, again, the water. Alright? So that's the idea. Now pay attention to a couple of things. First of all, this reaction must be taken place under heating. And here we will use heat under reflux. Okay? Secondly, we need to use dilute sulfuric acid. Now, if you remember, for esterification, if you go back to here, for esterification, we use concentrated sulfuric acid. However, for the acid hydrolysis of ester, we use dilute sulfuric acid. Now, the reason is because the reaction is reversible. So, meaning that the acid and the alcohol, they are able to undergo esterification and going back to the ester again, right? Now think about it. If we use concentrated sulfuric acid, which is a very good catalyst for the esterification, then do you expect to see you have a lot of acid and alcohol that can be formed from ester? No. If you use concentrated acid, these two will be very likely to react and go back to the ester, meaning that the reaction takes place with a very low yield. Okay, so this is the reason why we will use dilute sulfuric acid. Now, the third thing, actually, I have already mentioned. This is a reversible reaction, so we never get 100% yield. Okay, it always having some ester left unreacted. Okay, so this is the acid hydrolysis. Now let's look at alkaline hydrolysis. Now for alkaline hydrolysis, this time we will use sodium hydroxide instead of acid. And this time sodium hydroxide is the actual reactant rather than the water. So you see here we have a hydroxide ion instead of water being the reactant. And as the reaction proceeds, again we have to split the ester bond, so we will cut it here. Okay? And this time, the OH minus will be inserted into the carboxyl group here. Okay? Now actually, the idea goes like this. Sorry, I should put it this way. So as the reaction proceeds, it will generate ethanoic ion and the alcohol. Okay? Now you can understand this by thinking about, okay, this reaction is supposed to give you carboxylic acid and alcohol, right? This is what the hydrolysis means. You want to convert the ester back to the carboxylic acid and alcohol. Now you can think about it this way. The reaction does give you ethanoic acid and alcohol, but if you form ethanoic acid and the ethanoic acid is exposed to a strong alkaline medium such as sodium hydroxide, then the ethanoic acid form will immediately react with sodium hydroxide, forming ethanoic ions, right? So the idea is like once you form the ethanoic acid here, then it will immediately react with sodium hydroxide to form ethanoic ions. Okay, this is a simple neutralization reaction. Okay, so this is the reason why you don't expect to see ethanoic acid form after the alkaline hydrolysis. You should have ethanoic ions. Okay, so this is the difference between acid hydrolysis and alkaline hydrolysis. Now also you may look at the arrow here. This time we use a single-headed arrow because for alkaline hydrolysis the reaction takes place irreversibly, which is different from acid hydrolysis. Okay, but something that is similar is that for both acid and alkaline hydrolysis we must heat it under reflux to speed up the reaction. Okay, especially when ester and water is not particularly miscible with one another. That's why we have to heat it under reflux to increase the contact between the ester and the aqueous solution of sodium hydroxide or the sulfuric acid. Okay. Now here, under alkaline medium, carboxylic acid produced after hydrolysis immediately converts into carboxylic ion. Okay. But you may say, sir, I want the carboxylic ion back. I want the carboxylic acid, not the carboxylic ion, right? So actually, after the alkaline hydrolysis, we have to do one more step, which is to add excess dilute sulfuric acid. Okay. Now this excess dilute acid will first neutralize all the remaining sodium hydroxide, and once all the sodium hydroxide has been neutralized, excess acid is able to convert the ethanoic ion back to the ethanoic acid molecule. Okay, so this is what we want. So that's why when you undergo alkaline hydrolysis, if you perform alkaline hydrolysis, you need to do two steps. One, you heat under reflux with sodium hydroxide, and after that, you have to add excess dilute acid to convert the ethanoic ion into ethanoic acid. Okay? Now, we try to compare the two reactions, and actually we have two choices. Which one is better? In general, we would say alkaline hydrolysis is better. The reason is because, first of all, the reaction is irreversible, so we can have more esters. So the yield is higher. Okay? And secondly, it is easier to separate the alcohol from the resulting mixture. The reason is because here the ethanoic ion actually exists as sodium ethanoate, okay, and which is an ionic compound, it's an ionic salt. So an ionic salt would be having a higher melting point than the alcohol, right? So after the reaction, we have these two. If you want to separate them, then we can simply undergo a distillation, and you will expect to see the alcohol will be distilled off, and it's collected, all right? And after separating the alcohol from the mixture, what we can do next is to convert the ethanoic ion back to the ethanoic acid, and this time we can again perform another distillation or some other separating method to get ethanoic acid out of the resulting mixture. So basically, it is easier to separate the product if you use alkaline hydrolysis. For acid hydrolysis, you will form ethanol acid and alcohol, and these two, the boiling point are relatively similar than that in the alkaline hydrolysis. Okay, so that's why the separation is a little bit more difficult when compared to alkaline hydrolysis. Okay, it's easier to separate alcohol from the resulting mixture because carboxylate ion has a higher boiling point and less volatile than the alcohol. Okay, so we have two advantages of doing alkaline hydrolysis over acid hydrolysis. Okay. Now, amine and amide, all right? So first of all, the general formula for amine and amide. Now, let's focus on the amine first. Now, amine, you can understand it as having an ammonia molecule, which is like this, and we try to replace the hydrogen atom by the AQ group, okay? For example, we can replace one hydrogen atom into a methyl group, for example, CH3 and H2. So this one is an amine, okay? We call this one methylamine or methanamine. Okay, methylamine or methanamine, all right? Actually, we can have even more AQ groups. We can have 2 CH3 groups, we can have even 3 CH3 groups, okay? Or you can have like a C2H5, C3H7, it doesn't matter, okay? So this is what we call amine, all right? Despite of replacing hydrogen atom by AQ groups, actually they share very similar chemical properties when compared to ammonia, okay? First of all, amines, they are base. They are all bases, okay? And because they are able to dissolve in water, they are also alkaline, okay? So they are bases as well as alkalines, okay? So you would expect to see amine can actually react with acid in a similar way as ammonia. So bear in mind, amines are alkalines, bases, okay? Now, here I use the word primary amine is because we try to focus on amine with one AQ groups only. Because if you have 2 AQ groups, the naming is not required. But anyway, you need to bear in mind, even though it has 2 AQ groups or even 3 AQ groups, they react in a similar way as ammonia, okay? Or at least you should be able to recognize that that is an amine, okay? So it's like, for example, this one. Even though I have something like this, okay? Very ugly compound, but you should be able to recognize that it is actually amine. Just having all the hydrogen atom of an ammonia molecule replaced by the AQ groups, this is an amine. This is basic, okay? At least you need to know this. You will not be asked about the name, which is very complicated. Okay? Now the functional group here is amine group or amino group. Both are acceptable, amine group or amino group. And they are colorless liquid except methanamine and ethanamine. So basically starting from 3 carbon, then the amines are liquid. Okay, these two are gas. Okay? And meaning that they have relatively high boiling point when compared to other homologous series, like propane. Even propane with 3 carbons, they are still gas. But here, with 3 carbons, the amine are liquid. Okay? And for gaseous amine, they have a similar ammonia smell. Okay? For liquid amine, they have a distinctive fishy smell. So actually, if you go to the wet market, when you walk past the fishery market, the fish market, right? You got that fishy smell, and that fishy smell is actually some volatile amines. Okay. All right. Now let's talk about amide. Amide. So amide, we actually did see this one before when we talk about the reaction of carboxylic acid. We say that carboxylic acid can react with ammonia under heating to form amide. Okay, and amide, you need to focus on its functional group, which is this one, C double bond O with an N. C double bond O with an N. Okay, so it's sort of like a carboxylic acid or an ester. It is having a CO double bond and then connected to something else. And here it is connected to an amine, right? So here, this situation where we have an NH2 here, so this part is coming from ammonia, and this one we call an unsubstituted amide, because there is nothing attached onto the nitrogen except this carbon, right? But here, you see, when one of the hydrogen atom on the amine is replaced by AQ groups, this one we call it N-substituted amide, okay? Now, in the syllabus, you need to know how to name this one, but you need to be able to recognize that these two are amides, okay? So when I give you complicated molecules, if the question gives you complicated molecules, all you have to focus on is whether you can see C double bond O and then the C connected to a nitrogen atom. If that is the case, then they will be amide group, amide functional group, okay? The functional group amide, okay, and they are colorless and oily liquids. So even though the first member of amide, even though the first member of unsubstituted amide, they exist as a liquid. Okay, meaning that amides have a very high boiling point when compared to other homologous series. So they are odorless except methanamide, they smells like ammonia. Okay, now let's talk about the physical property, first of all with amine. So for primary amine or even secondary amine, they are able to form hydrogen bond between themselves. So amine, like I said, they have a relatively high boiling point when compared to other homologous series. However, the hydrogen bond between nitrogen and hydrogen is actually weaker than the hydrogen bond between oxygen and hydrogen. So amine, they have a lower boiling point than alcohol. Okay? And the reason why the hydrogen bond in amine is weaker is because nitrogen is less electronegative than oxygen atom. Okay? Now this is how the formation of hydrogen bond between the amine molecules. Okay? Now for tertiary amine, that means something like this. It does not have hydrogen bond between themselves because they do not have hydrogen atom attached to the nitrogen atom directly. Okay? Okay, for unsubstituted amide or N-substituted amide, they can form hydrogen bond between themselves. Okay? And the hydrogen bond is very extensive because not only the oxygen atom from the carbonyl carbon can form hydrogen bond with other amide, but also, the nitrogen here with two hydrogen atom, again, can be used to form hydrogen bond with other amide molecules. So in fact, among all the homologous series that we have learned, amide can actually form the most extensive hydrogen bond between molecules. Therefore, amide has the highest boiling point among all the homologous series that we have learned. Of course, we are comparing compounds with similar number of carbon. Okay? So that's the idea. Just some small remarks here. Amides are even denser than water, and amides are very much soluble in water because of the extensive hydrogen bond. Okay, so these are the physical property. Now let's talk about the chemical property. Now this part, I would say, the most difficult chemical reaction in organic chemistry. Okay, hydrolysis of amide, the most difficult one. The concept is pretty much the same as the hydrolysis of ester, but the most difficult part is you need to pay attention to how different parts, how different functional group, or how different products react with the given condition. Okay, so let's have a look. Again, hydrolysis of amide, we try to cut an amide So where do we cut an amide? Where do we cut an amide? Of course, we will cut it at the amide bond. At the amide bond. So here, this is the amide bond, and this is the part that we are going to cut it. Okay. Okay. And when we cut an amide bond, then we will expect to see the left-hand side will become the carboxylic acid, the right-hand side will become the amine or the ammonia. Okay? And we will cut it using water, again, because it's hydrolysis. So you will expect to see the OH from water will be plugged back to the carboxylic acid, and the H from the water will be inserted back to the amine or ammonia. Okay? Now, again, we have two types of hydrolysis, acid hydrolysis and alkaline hydrolysis. So let's have a look at here, acid hydrolysis of amide. Now here, even under acid hydrolysis, we are trying to split it into two types, which is unsubstituted amide and N-substituted amide, because they give us slightly different products. So let's have a look. Here, but don't worry, the concept is the same. The concept is the same. Now here, unsubstituted amide, first of all, we need to know where do we split it. So we split it over here, right? We split it over here. Okay? So when we split it over here, then the left-hand side, we will expect to have ethanol acid. We will expect to form an ethanol acid on the left, which is here, okay? The OH obviously coming from water, that this is the ethanol acid. Now here, when we cut it at the amide bond over here, you will expect the hydrogen atom is inserted back to the NH2, forming ammonia. So we should see ammonia here, okay? But it is not just ammonia, instead it is ammonium ion. So what is going on here is that, again, you need to pay attention to the acid-alkaline nature of the product. You see, ammonia is supposed to form after hydrolysis, right? But you know ammonia is a weak alkaline. And when you have an alkaline form in an acidic condition, you will expect to see the ammonia will react with the acid to form ammonia. Okay, so you will expect to see the ammonia reacts with acid to form ammonium ion. Okay, so this is the reason why we should expect to see ammonium ion form instead of ammonia. Okay, for ethanol acid, it is fine because ethanol acid can obviously exist in an acidic condition. Okay, so this is the reason why when we write down the chemical equation, we will also have the H plus here. Okay, in order to balance the equation. All right, and here the reaction is one directional, so it's irreversible, and this reaction also requires heating under reflux. Okay. Now, what if we have a N-substituted amide? Actually, the concept is the same. We cut at the amide bond, and then OH is inserted back to the ethanol acid, so obviously forming ethanol acid. And here, this part, we will have a hydrogen atom inserted back to the nitrogen atom, forming the primary amine, the methanamine. Okay, but again, methanamine is alkaline, right? Like I said, amines are alkaline. So once you form the ethanamine, CH3NH2, okay? Once you form a methanamine, it will react with H plus to form, okay, this one, okay, methyl ammonium ion. We call this one methyl ammonium ion. Now this is one word. I don't have enough space. This is one word. Okay, let me put it here. Methyl ammonium ion. Okay? So this is the product, And we call this one acal. This is the general name, okay, acal ammonium ion. In this case, the specific name is methyl ammonium ion, okay? Actually, it shares a very similar concept, okay? All right, so that's why if you look at the sentence here, I will say that unsubstituted amide is hydrolyzed into carboxylic acid and ammonium ion. Whereas here, N-substituted amide is hydrolyzed into carboxylic acid and acal ammonium ion. Okay, so that's the idea. That's why you really have to focus on the acid-alkaline nature of the product, and you have to think about which form or whether or not the acid or the alkaline can actually exist in the given condition, or will they be neutralized to form the corresponding ions. This is what you have to think when you are writing equation for the hydrolysis of amide. Okay, so that's why I would say this part will be a little bit more complicated than before. Okay. Now let's look at alkaline hydrolysis of amide. Similar to ester, amide can be hydrolyzed either with an acid or alkaline. So in this case, probably we will use sodium hydroxide. Now, when we use sodium hydroxide, the reactant will be the hydroxide ion. Okay? Now, here, for unsubstituted amide, similar idea. We split it at the amide bond. We cut it at the amide bond. Okay? So, we will have OH inserted into the ethanol acid, forming ethanol acid, of course. And then the H will be inserted back to NH2, forming ammonia. Okay? And then we have to check whether ethanol acid and ammonia can actually exist in an alkaline medium. So we have to check whether there will be a neutralization reaction between the products and the given condition. So it turns out that, yes, because this is an alkaline medium, so you're supposed to form an ethanol acid, but it will react with the alkaline medium, the hydroxide ion, to form the ethanoic ion. Okay? And this is the reason why you should put down ethanoic ion here instead of ethanoic acid. Okay? Now, ammonia is okay to exist in an alkaline medium because it is a weak alkaline. Okay? So that's why you see here, unsubstituted amide is hydrolyzed into carboxylic ion and ammonia. Alright? So that's the idea. Similar idea for N-substituted amide. For N-substituted amide, again, we will cut it at here, okay, forming an ethanoic ion and acal amine, okay? So basically, we insert the hydrogen back to the nitrogen here, then it gives rise to an acal amine. In this case, methanamine, okay, or methylamine, okay? So that's the idea. That's the idea. Okay, so that's it for all the reactions. Okay, so congratulations, you have learned all the chemical reactions in organic chemistry, almost. I think you still got one, which is saponification. And also another one, which is condensation polymerization, which is at the later part, not in this video. But those are actually not some brand new reactions. They are actually based on the hydrolysis of ester and also condensation of ester and amide, something like that. So technically, you have learned all the concept of the reaction actually. Okay. Now let's do some practice question on page 48. Again, pause the video, try to do the question itself, and then we check the answers. And again, at this time, we need to look for the products. We need to look for the products, not just the organic products. Any product that we will form, you need to include them. Okay? Pause the video and try it yourself. Okay, let's check. Let's check. Okay, this one. This one is an ester, methyl propanoate. we are given with an acidic condition, heat under reflux. So there has to be an acid hydrolysis of ester. So we will cut it here. Okay, this part on the left will give us propanoic acid, CH3, CH2, COOH. Okay, and then the right hand side here should give us methanol, CH3OH. Okay, the two products. Now here, this is again an ester, but this time we have an alkaline medium. So again, we will cut it at the ester bond. On the left hand side, we should have, on the right hand side first, we should have an ethanol. Okay, we can put down the ethanol first. Okay, and on the left hand side, we're supposed to form a benzoic acid, but because it is an alkaline medium, so the benzoic acid will subsequently neutralize to form a benzoic ion. So we should have a benzoic ion here. Okay, we should have this one. Okay. Now this part is the very basic amide, methanamide. Then we will cut it here. This is an acid hydrolysis. So the left hand side we should have a methanoic acid. And on the right hand side it's supposed to give us an ammonia molecule, but because this is a highly acidic environment, so we would expect to see ammonium ion instead of ammonia. Okay? Now down here, first of all, you need to recognize that this is an amide. This is an amide. If you're not very comfortable with this one, you can draw out the expanded structural formula for the amide group. Okay, which is like this. This is the same as this one. Okay? We do the hydrolysis over here. Okay? This is an alkaline hydrolysis. So the left hand side here is supposed to form a benzoic acid, but because of the alkaline medium, it should give us a benzoic ion. Okay? And on the right hand side here, this is an amine, which is okay to exist in alkaline medium, so you can just simply copy. Okay, that's the idea. Next one, we have a cyclic ester. Okay, before we did talk about how do we form a cyclic ester from a compound where there is two functional groups, each at the terminal of the chain, where the head and the tail can kind of coil and then kind of react with each other, forming a cyclic compound, right? Here, we just do the opposite. This time, we try to split open an ester, a cyclic ester, okay? In this case, it will give us one single compound with two functional groups at each side of the terminal, okay? Each terminal of a chain, okay? So, we will cut it here, then we can count 1, 2, 3, 4, 5 carbon, okay, 5 carbon. So 1, 2, 3, 4, 5, okay, 5 carbon. And one would be the alcohol, right? One would be the alcohol. Another one will be the carboxylic acid, but because this is in an alkaline medium, so it actually exists like this, exists as a carboxylate ion. Okay? 1, 2, 3, 4, 5 carbons. Okay? Now this one is very complicated, as you can see, because you see there are more than just one functional group. There is actually an amide group here, amine group here, and then a carboxyl group here. So 3 functional groups, of which they have specific acid-alkaline property. So you need to pay extra attention as to how they look like after the hydrolysis. Now, for hydrolysis, it takes place at the amide bond here. Okay, so you should have 2 molecules left and right. Okay, let's focus on this one. So once you cut it open, this one will form carboxylic acid, which is okay to exist in acidic condition. So we can put down. Okay, but for this part is an amine. Amine in acidic condition, it should exist as an alkyl ammonium ion. So this is one of the products. Okay, the left hand side goes to here. And then another one, which is on the right hand side. So once you split the amide bond, then the nitrogen here should form, this part should be an amine, right? Okay. But again, once it forms an amine, it will quickly react with the H+. So you should expect to see an alkyl ammonium ion. Okay? So here you see, wow, so many H's, right? So many H's. But if you pay attention, one of the hydrogen atom inserted is coming from the hydrolysis. Remember, one hydrogen atom will be given back to the nitrogen atom. Another hydrogen atom is introduced when the amine reacts with the acid catalyst. Okay, so this is how it looks like. And then the remaining carboxyl group can just stay the same. It doesn't matter, right? Okay, so these two would be the two products. Okay. All right. Yeah, this one will be quite difficult because you need to take care of more than just one functional group, two functional groups, but here 4 functional groups, acid, alkaline behavior. Okay? And the last one, this is just a very typical amide. Okay? So we will cut it here in an alkaline medium, then it should give us this one, and then okay, we have a propanoic ion, and then we have a ethylamine or ethanamine. Okay, all right. Okay, let's move on to the multiple choice here. Now, which of the following reagent and conditions are necessary to convert ethyl ethanoate to ethanoic acid by alkaline hydrolysis? Okay, so we try to write down the equation and try to understand the situation. Ethyl ethanoate, right? So CH3, C double bond O, CH2, CH3. So alkaline hydrolysis into ethanoic acid, like this, okay? So hydroxide ion and heating will be the condition. Okay, so in this situation, what reagent and conditions are required? So first of all, heat under reflux must be required, okay? You see heat. And dilute strong acid, such as sulfuric acid, this one you see 8, sir. Seems no need, Lord. Seems no need, because we are doing alkaline hydrolysis, right? But bear in mind, if you do alkaline hydrolysis, actually you should not have ethanoic acid. Instead, you should have ethanoic ion, right? So here you should expect to see you form ethanoic ion, and after that you have to add acid to regenerate the ethanoic acid, right? So it's like 2 steps, 1, 2. So that's why, even though you are doing an alkaline hydrolysis, because you want to have the ethanoic acid instead of ethanoic ion, so that's why you need to also use a strong acid. Okay, so this one is necessary. Now also strong alkaline here must be required because you need to use it as one of the reagents. So the answer is D. All 3 reactants or conditions are necessary. Okay. Now here, so this basically to test you whether you know how to split a compound at the ester bond and the amide bond. Okay, this one, if the organic compound was completely hydrolyzed, and no matter acid or alkaline, how many products will be formed? How many products will be formed? Okay, so first of all, you see this one is an ester, so you cut it here, you cut it over here, and then you also check you have another ester over here, so you cut it. Okay, and just right now here we have an amide, so we cut it here. All right, and you also check, no, there is no other products, right? So altogether, 1, 2, 3, 4. 4 of them. Okay, so the answer is C. Okay, so this is to test you whether you can recognize all those ester bond and amide bond. Okay. All right. Question 4. Hydrolysis of ester and amide can produce carboxylic acid. So write a balance equation for the following hydrolytic reaction. Alkaline hydrolysis of ethane amide. Okay, so first of all, ethane amide should be this one, CH3, CH2, just ethane. So CH3, C double bond O, and H2, like this. Okay, this is ethane amide. And a balanced equation, alkaline hydrolysis, you need to add hydroxide ion, one-headed arrow, to form ethanoic ion and ammonia. Okay, so this is the equation. And then acid hydrolysis of propyl ethanoate. So the ethanoate is here, C double bond O, and then the propyl group, so CH2, CH2, CH3. So this is the propyl ethanoate. So acid hydrolysis, remember, if this is acid hydrolysis, you actually add, hold on a second, I got a phone call. Why?我要 check 翻先，知我而家冇資料喺手，所以係啦。不過其實應該咧，嗱你之前係介紹咗渣打嘅，不過咧就而家都要睇渣打，但係我係咪經理嗰個原生好似唔係，因為我一開始就冇用到，跟住之後再私底下揾渣打嘅同事，咁係啦，我就應該唔係直接揾你介紹嗰個渣打。Okay, sorry, I'm back. Right, so acid hydrolysis of ester. Remember, the reactant is not an acid. Instead, it should be a water. Because like I said, in this case, acid is actually acting as a catalyst rather than an actual reactant. So it should give us, so you've got to cut it over here. It should give us ethanoic acid and propanol, okay, a propanol, okay? Alright, is that okay? Of course not okay, because remember, acid hydrolysis, you need reversible sign. This is a very common mistake when students learn about hydrolysis. Because now overall you have 4 hydrolysis, right? 4 hydrolysis. Acid hydrolysis of ester, alkaline hydrolysis of ester, acid hydrolysis of amide, alkaline hydrolysis of amide. So all 4 of them, you realize that only acid hydrolysis of ester would be reversible. The other 3 would be irreversible. So make sure you memorize this. Okay? Now B here, you may notice the two reactions can generate ethanoic acid, right? You notice that both reactions can generate ethanoic acid. So which method would you prefer to synthesize the ethanoic acid? Explain your choice. So the only choice is actually the alkaline hydrolysis. So you must choose alkaline hydrolysis. Okay, because only this reaction is irreversible. So it results in higher yield of ester, of ethanoic acid. Okay, so I think you should only be choosing alkaline hydrolysis. I don't think you can choose acid hydrolysis. Okay, it is generally agreed that alkaline hydrolysis is better than acid hydrolysis. Okay. All right. So that's the idea. So that's it for the functional group chemistry. So you see this chapter. Now I'm not sure if you recognize this is part 1. So so far we have discussed from the second video to now the 6th video. We have already covered these two, okay, which are the main dish. All right. Now I'll see if we have further videos. If that is the case, then for the part 2 we will be focusing on these two. Okay. Now for organic synthesis, these are the application. Okay, the application. We don't really learn new reaction. It's more like the application of what we have learned in functional group chemistry. And here, these are some specific examples of organic compounds, of which we will delve into more details, learning about what are these organic compounds. Okay. So anyway, we will stop it here today. Stay tuned and bye bye.